Hello, everybody, and welcome to Lecture 1 and 2 for General Chemistry. I'm very excited to be actually starting this finally. If you've seen the shorts on YouTube I've made, then you might already be familiar with these topics. And if you haven't seen the YouTube shorts yet, I highly suggest you go do watch them because all these topics are kind of like shortened down in little easy to understand parts. And this video is for expanding upon that. So I'm going to launch into Lecture 1 and 2, and I'm going to explain everything as detailed as possible, the best I can. And if you do have any questions, please leave them in the comments, and I will do my best to answer it as best as possible. And if I can't answer it in a comment, I'll try to answer it in a YouTube short possibly, or maybe I will make a video in the future about that topic to go into more detail about it based on a comment you leave or a topic that I think just needs its own video, because there might be a video like that in the future. So getting into it, we have here chapter E. So this is basically your base. This is the foundation of General Chemistry. General Chemistry 181 is what we're starting in. There's also earlier General Chemistry classes like 111, which is more high school class. This is kind of like high school chemistry, but it just dives into it a little bit deeper, and it goes further because the 181 series, which I will be teaching first, is preparing you for a higher chemistry degree or a chemistry minor. So when you're watching these videos, please keep that in your mind, and just know that this might help you out if you're trying to look at this for like high school chemistry, but I will be going more in depth than needed. So don't think that you're going to have to know all of this if you're looking at this from a high school standpoint, but do dive into this further, into this topic. So I'm not claiming to be an expert at anything. I am a fourth year biochemistry major, but obviously other people might explain it better than me, and so it's best to go to tutors, it's best to go to people in your college, it's best to ask your friends, your professors, and it's best to go watch other YouTube videos as well. But I'm going to try my best to explain it, but I urge you to seek out other sources as well, because having different POVs and having different people explain it to you is very important. So with that out of the way, and this is the only time I'm going to go into this, so sorry for you hearing me out. Now we can actually get into it, and then every following lecture video I'm just going to get into it as well. So starting in chapter E, it's the essentials, units, measurements, problem solving, and we're starting with the units of measurement. I'm going to skip over a couple things, but I'm going to explain it the best as possible for what you need to know. This is just a general overview of everything. So electric currents, amperes, are not going to be really used until later, and I don't think I've ever used candelas, so I don't think you got to worry about that. But again, I'm a biochem major, so I'm going off of what I know and what's been best for me for my major, and based on what my professors have said. Right? So keep that in mind. So we have length, mass, time, temperature, and the amount of a substance. If you've watched the shorts, you'll kind of be familiar with this, and you'll especially be familiar with moles here. Not the actual moles, the squeaky little guys, but moles are a way to describe the amount of like atoms. So those are going to be very, very important. Once we get to general chemistry too, I'm going to be making my own stuff, but I don't have any notes of my own from General Chemistry 1, which is why I'm using his slides. I will not be going off of professor's slides for anything other than Gen Chem 1. I don't want to leech off of their stuff. Kelvin is going to be very important. One of the YouTube shorts I did goes into how to calculate between Kelvin and Celsius. That's going to be the main thing that you guys need to learn how to do. So at 0 degrees Celsius, it's 273.15 Kelvin. Normally you don't have to use the 0.15, but if you want to be exact, then you guys are going to have to use 273.15, all right? You guys are not going to be using Fahrenheit a lot. There's going to be some initial conversions most likely for you guys to learn how to calculate between Fahrenheit and Kelvin, but the most conversions you're going to be doing is between Celsius and Kelvin. Kelvin is important in chemistry, and it's going to be a lot more widely used. It's more accurate. So the only difference between the Celsius scale and the Kelvin scale is the position of 0. So if we look here, between 0 degrees Celsius and 100 degrees Celsius, there is a difference of 100, right? It's the same thing for kelvins. 273 is the quote-unquote 0, and then it goes to 373. If you're asked on a problem, or what is the temperature in Kelvin, if there's a 5-degree change in Celsius, you would take 273 and you'd add 5 to that. The only difference between these two is where it starts at 0, right? Fahrenheit is its own thing. Fahrenheit's kind of weird, so we're not going to look at Fahrenheit that much. If you want to learn how to convert between Fahrenheit, there is the conversion at the end of my YouTube short, or I'd recommend looking it up. But again, I've never converted between Fahrenheit, so I don't think you're going to have to do that. I don't think you're going to have to do that unless you're asked to initially once or twice, and then you'll be good to go. Going down here to absolute 0, minus 273, 0 Kelvin, minus 273, negative 273 degrees Celsius. This is the big one. This is the one that you're going to be using the most. That, and then converting between grams and meters, I think. And here's the conversions between the units of temperature. Again, very important to know Kelvin and Celsius right here. This is moles. This is a perfect little example right here. So 1 mole, also written MOL usually, is 6.023 times 10 to the 23, or 6.023 e to the 23. These are the exact same thing, but the biggest thing you guys got to know is scientists are hella lazy. We are extremely lazy. So we're always trying to find shortcuts that make our work a little bit more efficient. So that's very important. So instead of writing times 10 to the 23, E replaces the times and 10 and signifies that whatever number's after it is to the power right here. So instead of writing this, we could just write this. It's easier, it's faster. Your hand's gonna get tired after writing times 10 to the whatever after so many times. It's important to be able to recognize these shortcuts, but also keep in mind that on exams and everything, I would suggest writing it out this way instead of like e to the 23, because your professor, while they understand this, might prefer it this way. So it's all about asking them to see maybe what they prefer. Diving into it also, this is a fine example of scientific notation. So x times 10 to the power of something is an example of scientific notation. If we did not write x times 10 to the power of something, we would have this horrible thing right here. And if you think your hand was hurting after writing this so many times, your hand was definitely going to be hurting after writing all those zeros. So this is like the first step, and then you can convert it, and then you can even go shorter. So how do we know that 23 is here? The 23 right here has nothing to do with this number right here. So it's saying that if the decimal point is right here, then there is 23 spaces. There's 23 spaces before it gets to right before the 6. So everything I've highlighted here, if you imagine a decimal point right above my cursor, it goes 1, 2, 3, 4, all the way over to the right side of the 6. So that means we have 6.023 times 10 to the 23. So there's 23 little decimal points. And this is a really big number. So if this is positive, this means it's a really big number. So if we go down here, we can even see it a little bit better. So 1.83 E8 inches. So don't say E to the 8, but just E8. And then the decimal gets moved over here. Remember, positive exponents are for big numbers. Moving the decimal point to the left means that it's positive. It's positively left, right? So think about PL, positively left. That's very important to know. I always like to try to think of little metaphors or something that can help me, and sometimes they can be really silly, and the sillier it is, you can kind of remember it better. So positive left or positively left. PL could mean pickled lemons, and you know pickled lemons, PL, positive left, positive exponents are for big numbers, and it goes to the left, right? So this is very important, because when you take this and you're asked to write it out fully, because you might be asked that, then you remember if it's positive and left, when you're making the exponent, then you'll just take this decimal point and go 8 to the right, and then you'll have this big old number right here. So for small numbers, instead, you're going to finding this decimal point here, and you're going all the way to the right until you get to the first whole number here, because you're trying to make a whole number. You're trying to make a very nice looking whole number. This is very nice to look at. This is not. So you take 11 steps towards the right, and because you're going to the right, you get negative. So negative right, NR, let's see what we can figure out with NR, noodles, ramen. Noodles and ramen. There you go. So if we know noodles in ramen, NR, negative to the right. So if we get negative to the right, we see E negative 11, or times 10 to the negative 11, means that when you want to write out this number, you see the negative sign, which means you need to go to the left, because remember, you got to go to the opposite when you do it. So when you make it, you know it's negative. You know you went to the right to make it, so then you go to the left. So to go along with scientific notation, there's an even easier way. So this table is very important, and it will be your absolute friend. I swear to goodness, you guys should print this out and just keep it with you, especially if you're going through the 181 series, because this will tell you, and you guys should memorize these. These are going to tell you the scientific notations, but in word form. So we should already be familiar with some of these, like centi represents like 100, right? So in this case, centi is put here as making it a smaller one, but we also know that centi can represent 100 usually. A milli represents 1,000 millimeters in 1 meter. So these are all prefixes, which means it comes before the word. So it would be like centigrams, decigrams, kilograms, megagrams, gigagrams, teragrams, or in the modern age we could use bytes. We got kilobytes, megabytes, gigabytes, terabytes, right? Terabytes are one of the biggest ones right now. Each of these prefixes could go before every single unit of measurement. So we could have milliliters, microliters, centiliters, centigrams, milligrams, micrograms. Moles, I don't think would have any of these prefixes though, because it's its own unit. But you guys got to remember this. Personally, I've only used kilo to nano for the most part. Right here, these are the ones that you're going to want to memorize. On the exams initially, you guys are probably going to be tested all the way from femto or F all the way to giga, and which is why the professor said you should know these ones. I highly recommend practicing, writing out, knowing that these symbols mean what they mean, and also knowing other things like this, the conversions between everything. So it's going to be very hard. Converting in between units of measurement is going to be the first big thing that you do in chemistry. It's very important, and general chemistry is all about setting you guys up for success. I personally wish that I paid more attention and practiced these conversions way more when I was in Gen Chem, because I have struggled a lot because I didn't pay attention enough. So I really, really, really urge you guys to, again, look at other resources and make sure you guys are practicing these a lot, because even when I'm tutoring people in the chemistry tutoring center here at my college, a lot of students in Gen Chem and Gen Chem 111 are struggling with conversions. Prefixes are useful for converting between large and small numbers, because now that we have these prefix modifiers, right, because the K means kilo, right, then we can use this and we can start canceling out units of measurement. You're going to be given a problem like this, like convert 2.35 kilometers into meters, M. What is best? There's a bunch of different ways you can do this, but what I think is best is doing exactly this. You take your number that was given, you put it over 1 in order to turn it into a fraction, right? Because every single whole number can be written over 1, because everything on top divided by 1 is just going to be itself. So this is still 2.35. And then you're going to multiply it by 1,000 meters over 1 kilometer. Kilometers are going to cancel out. The units across from each other are going to cancel out, leaving you with just meters, because there's nothing for meters to cancel out here. Then you're going to multiply across. So you could rewrite this as 2.35 times 1,000 divided by 1 times 1. So you can just multiply everything on the top, multiply everything on the bottom, and divide the top and the bottom. And then you'll get 2.350 meters, or go 1, 2, 3, 2.35 E3, or 10 to the 3 meters. All right, let's do it again. This time we're taking something small and converting it into something bigger. So we have 2.35 millimeters over 1 times 1 meter over 1,000 millimeters. So there's a big difference here. So now you got to think, how would I know to put something on the bottom? Well, we're always trying to cancel out the unit here. So if you have millimeters here, then you have to have millimeters on the bottom. And what are you trying to get? You're trying to get meters. Well, we know that there's 1,000 millimeters in 1 meter, so we can write 1 meter on the top. Our millimeters cancel out because they're across from each other, and we multiply everything on the top, we multiply everything on the bottom, and we divide it, and we get this answer, and we can move the decimal over to the right, negative right, noodles and ramen, and we have E negative 3. Up here, remember, kilometers, we needed meters, 1,000 meters in 1 kilometer, we knew that, and we multiplied everything on top and bottom, and we got this, right? So it's going to be very hard. I'd recommend you going through every single unit of measurement and practicing this, because that's going to be how you're going to succeed. And once you get all of this, everything else is going to be so much more easier, and you guys are going to go into the lab and you're going to thank yourself for practicing this. I swear to goodness. Also, keep in mind that this is going to be kind of silly, but liters can also be written as centimeters cubed. So centimeters cubed is the volume. Remember, the volume is length times width times height. That's why this is a 10 by 10 by 10. This is why it's centimeters cubed. So 1 liter is equal to 1,000 centimeters. You can't really use that between conversions and something else, and it gets kind of a little more complicated. But if they give you 1,000 centimeters and you're trying to convert that, just know that it's equal to a liter. And you know how to convert between liters and milliliters and centiliters if you've been practicing. And then because you know this, you can make a line of these conversions. So eventually you'll have like 5 or 6 of these all in a row, and then you'll multiply everything on the top and everything on the bottom and divide them. And it's going to be quite long. But that is it for lecture 1. So I'm going to go ahead and go and get lecture 2, and then we will continue from there.